Test. That looks better. Okay, suppose it works now. Well, that's interesting. And it's like, why can't Windows just stick with one device being the standard device? Why every, like, I don't know, every once in a while it decides the standard device is now a different device, even though nothing changed. Okay, so like Windows updates. There was an update that came yesterday. Okay, so let's repeat what I said. I was talking about the rendering equation, which is kind of important. As you can probably tell from the name, that it's a fundamental equation that describes the rendering process, or more precisely, it describes how radiance is exchanged between surfaces. Whatever radiance is, more on that in a couple of seconds. Just a quick refresher, what does this equation actually tell you? Okay, what does this equation actually tell you? Well, it tells you that the radiance, or for now, the brightness, which is not the same, but let's for now pretend that's the case. The brightness of an object is whatever it emits, that's the blue part, plus the sum, that's the integral, over all that it receives, that's the red part, times how much of that received quantity is reflected into the direction that we're observing that point. So that's kind of the overall idea. And the last thing that I explained in the last stream was the bidirectional reflectance distribution function. Okay, here it is. So what's the bidirectional reflectance distribution function? Well, this is this function that acts as a weight on the incoming radiance and on the outgoing radiance. And I explained the last time already that it's a little, the definition at first glance is a little bit counterintuitive. It's not just a weighting factor, it's not a percentage. It's this thing that depends on not the incoming and outgoing radiance directly, but on the incoming radiance weighted by the area foreshortening term, and then taking this quantity and the outgoing radiance and taking the ratio of the two derivatives. Okay, and I tried to motivate that this is basically the only reasonable way to go. Okay, so that's our weighting function, and this weighting function gets multiplied with the incoming radiance, and then we sum this all up. So now that I've mentioned this term radiance a couple of times, like, let's kind of get to the bottom of what this whole radiance thing is all about. To do this, we need to look a little bit at physical quantities. I mean, after all, that's pretty much optics, that's energy exchange that we're talking about here. So we need to get a little bit physical if we want to do physics-based lighting, which is what we ultimately want in global illumination. So first of all, what's energy? Well, energy is in joule, it's measured in joules. I mean, you know joules, right? Kilojoules, food, I don't know, whatever, right? In joules, it's just a fancy term for Newton meters, which term is just a fancy term for kilograms meters squared by second squared. Okay, so but regardless of the units, let's just call it joules, which is appropriate, and it's just easier to think about this, and it's just energy. And we're particularly concerned with the radiant energy. Of course, there's other things like potential energy and kinetic energy. There's all kinds of different things, but those are basically just different views on the same concept of energy. Okay, so, and there's also radiant energy. So that's, well, energy that gets radiated somehow. The trouble with this quantity by itself is that it's very specific, meaning that well, the radiant energy is literally a, how should I phrase this? It's a, I'm just trying to say it's a bunch of energy, but that doesn't make any sense. It's a lump of energy, right? It's something that has a certain effect that accelerates a kilogram, basically. Okay, so but what's the problem with energy? Is it's considering a very specific situation. Okay, so if we look at the next quantity, this concept becomes clearer that looking at just a specific situation is a problem. So let's look at the next quantity, and that is radiant flux in watt. You've heard watt before, right? Right, you know watts from, I don't know, your light bulbs or your LEDs these days, I guess, right? So, and what this is joules per second, right? If we just focus a second on the unit, it becomes obvious why that is more useful. Because energy is just some lump quantity, right? Whereas watts tells us like what's going on per second, what's going on right now, right? So that's a way more useful quantity to describe something, right? Because if you know that this, whatever, say, light bulb emits or receives a certain radiant flux, then you know that it receives some energy per second. And it doesn't matter how long the light was turned on, right? So for instance, if you think about when would I get joules? Joules I would get if I, for instance, turn on a light source and let it burn for a while and then turn it off and then compute what happened, right? So then I get a joules because then I have to multiply the radiant flux by, I don't know, 10 seconds that it was burning. But that's a pretty useless quantity because it changes the longer I leave this light on or turn it off, okay? So watts in that term is both is a more general specification, okay? And keep that in mind in general. The more like pers or the more divisions we do, I mean, per second is the same as divided by second, right? So the more of these pers we do, the more general we get, the more cases we can cover with this unit, okay? Okay, so now that's watts. Okay, so how much energy do we emit or receive per second? Okay, so the next thing is irradiance. So that's the first like super important quantity. So we'll have two quantities, or three to be precise. We'll have three quantities that are immensely important. One is irradiance, the next one is radiance that I already mentioned. More on that in a second. We need to build on top of a couple of things to get to radiance. And the third one is radiosity. Okay, so now for the first super important thing that we will need throughout this whole lecture, and that you generally need if you do physics-based lighting quite a lot, that is irradiance. And that is now watt per square meter. Okay, and whereas watt in turn is joules per second. So this is joules per second per square meter. Okay, so you get two pers. So it's more specific or more general to a wider range, applicable to a wider range of things. What does this mean, this irradiance thing? Well, since it's per square meter, it takes area out of the equation, like literally it divides it out, right? It divides area out of the equation. That means now we have a material property. We don't have a property of, say, a light source anymore, right? If we're talking about watts, I say this light source here, it emits so much energy per second. Irradiance tells us, well, this surface spot of that light source emits so much energy per second. And then, of course, per the overall thing emits this per square meter. Okay, so we're getting to a point where it's not just a piece of hardware anymore, but where it's literally a quantity that describes a part of the surface. Okay, so that is irradiance. It's watt per square meter, so it's the energy that gets emitted per unit time, per unit area. Irradiance. Okay, first thing to remember. Next one is radiant intensity. So this is now watt per steradiant. Okay, and while I guess if we just go back here, okay, so meters is something that you hopefully are familiar with. Square meters, well, sure, you're familiar with that. Seconds, of course. Well, joules, more tricky, right? But we all know how many joules, I don't know, an ice cream ball has, or we probably don't know it, but we know what we mean when we say this is like an ice cream scoop. That's how much joules it's got. So we have an intuition of all these things. Now, with the steradiant is that hardly anyone ever even heard the term steradiant. What the hell is a steradiant? Okay, so what it is, it's a solid angle. Well, that helps a lot because I suppose many of you haven't heard the term steradiant either. Solid angle either. So what's a solid angle is kind of an idea that combines angles with areas. Okay, and I've put a graphic here on that slide. I don't want to really go into the details, even though the functions are interesting, and we're gladly going through those in the exercise. But just as a conceptual idea, sometimes you're interested in what comes from a specific direction. Okay, so we had per second before, we had per unit area before, and now we want this per unit direction thing. Okay, this is important if you're thinking about emitting energy in all directions, right? Or just emitting energy in like a specific direction. So now we need to somehow normalize this idea of direction, okay? And that has something to do with the angles, hence it's called angle, right? Why is it called solid angle? Because it's like, it's sort of this, just like per square meter is like from a square meter down to a point, an infinitesimal point, and this is down from like a certain cone, an angular cone, down to, well, an infinitesimal small cone. It's just basically one direction, okay? And that's what a stereoradiant is, or what a solid angle is. It's a breakdown of the sphere's directions, right? Whereas the sphere is it's just a fancy term for all directions. Okay, so this here now is watts per stereoradian. Let me go one slide back. What was watt again? What was joules per second? So that's energy over time over a specific direction, over a stereoradian. So this radiant intensity tells us, let's just assume we're emitting energy. That tells us how much energy for a unit period of time do we emit into a unit direction. Okay. Notice how one thing is absent here. Again, a slide back. What is absent is this meter squared. So this radiant intensity is, again, for a whole object. It's not for a specific point. Now, if we want to get this in as well, this specific point thing, we end up with this thing called radiance. This is now watts, which is joules per second, per square meter per stereoradiant. Okay. So the bottom line, and in the top, there's the derivative function, which is basically just executing one of those derivatives one after the other. So every per is, of course, a derivative, right? So we get a bunch of derivatives one after the other. But what is this now, just conceptually? Okay, even if you're like overwhelmed with the whole calculus idea here, but the concept is actually what radiance is. That is energy that is emitted into a specific direction, stereoradiant, right? Into a unit direction per unit time, so every second or so, per unit area. Okay, and that's a very, very specific quantity, right? If I know this property of a surface point, right, I know a lot, right? I can tell for like this quantity, like the more pers I introduce, the more general this idea gets, right? And then for one direction, it might be different than for another direction. Or for one surface point, it might be different than for another surface point, okay? But I can now multiply this with time, or I could multiply it with the area of an object, or I could multiply it with a certain part of the sphere, say the hemisphere, like half a sphere, to figure out how much energy is emitted into all directions, okay? And that's what radiance is. What's curious about this thing, that radiance remains constant along a ray. So I send this out, and then we're always assuming that we have vacuum in between objects here, right? So that's an important assumption that we make. But if we make this assumption, since in an infinitesimal small cone, right? So this thing doesn't change. It doesn't diminish with distance. Okay, so we can emit this into a direction, and we'll receive it into a direction, and regardless of what the distance between the 2 points is. Okay, so that's radiance. Joules per second per square meter per stereoradiant, or simply watts per square meter per stereoradiant. Per square meter per stereoradiant. Yeah, that's correct. Okay, second important thing. So first was irradiance, second was radiance. And there's a relation between the two, between radiance and irradiance. What's missing in irradiance? The per stereoradiant, right? That irradiance is across all directions and radiance is into one direction. The way I used to remember this as a student was to just think about irradiance as the integrated radiance, which kind of makes sense because you sum up overall radiance direction, you get the irradiance. Okay, that's how I managed to remember the terms radiant and irradiant. Okay, so what's the third important term? That is radiosity. Like, what's radiosity? Here it is, and I simply give you an equation that relates all these terms to each other. So radiosity is on the left, and then in the center we got irradiance times a factor rho, which is the reflectance. So from this you can see that irradiance and radiosity have the same unit, because the reflectance is just a weighting factor, so it's unitless. So it's got the same unit as irradiance. The only difference is really that irradiance and radiosity are related by when you have an object and it reflects the light in a very unique way. Namely, in this case, as you can see, if you compare this equation here to the rendering equation, you see that the emission is gone. Well, never mind that emission, but you see that the BRDF here is gone. Instead, we have this factor here. The only situation where I'm able to take a factor out of an equation and plug it in the front is when it's constant, when it doesn't change with regard to the integration parameter. So this rho here is the BRDF. And the BRDF in this case appears to be independent of the direction. So if we have a BRDF that's independent of the direction and we integrate over all of these BRDFs, then we get a factor rho. Okay, the relation between the BRDF and the factor rho itself will be discussed later. Okay, so because even though it's constant, it still gets integrated. So it's not just the sum over all of these BRDFs. So, but we'll see. Well, maybe today I'll get to that point where I derive rho. But for now, this is just a factor that I throw in front, and this tells me like how much of, well, similar to the BRDF's intuition, how much of the received energy is actually reflected. For what objects does that make sense? For objects that have the property that the reflectance is independent of the direction, in particular of the viewing direction, okay, and sort of as well on somewhat independent of the incoming direction as well. I'm saying somewhat here because the incoming direction still shows up in this area, foreshortened term. Okay, so, but ignoring that part for a second, if you have an object where specifically it doesn't matter from where you look at it, you see the same brightness, or more specifically, you get the same radiance out, then you can do this. You can make the simplification here, and to make it even more simple, if you have a diffuse surface, because that's exactly what a diffuse surface is. A diffuse surface is a surface where the viewing direction doesn't change what I see. Okay, it's a surface that reflects energy into all directions exactly the same. Okay, so for a diffuse surface, we have this notion of a radiosity, and that is related to an irradiance via a simple weighting factor. And then, as you can see from the center of the equation to the right, the irradiance is related to the radiance by simply the integral times this foreshortening. Okay, and this whole foreshortening thing is why we can't just pull the BRDF in front, because it contains this thing here. So the BRDF sort of by definition depends on omega. So we first have to reformulate the BRDF into its constant and non-constant part. So it's part that doesn't depend on the angles and the part that does depend on the angles. If you pull that in front, the part that doesn't depend on the angles, you can then integrate over the independent part and you end up with rho. But again, more on that maybe later today or next Thursday. We'll see how fast I am today. Okay, but those are the three quantities: radiosity, radiance, irradiance. Okay, remember those. Even if you don't remember them right away, memorize them. Very important. Otherwise, you'll have tremendous trouble understanding any of the theory that's going to follow in the next, I would say, 5 streams. Okay, they all heavily rely on those concepts. And actually, what comes on top of that is pretty straightforward, but I assume that you get this. Okay, so that is all good and well, and it's all theoretic, and well, it's all physics and stuff. And aren't we doing computer science here? Well, the truth is, it's all kind of related. But nonetheless, we can take a step back and say, well, okay, nice that we got all these physical quantities, and we got this whole rendering equation thing, and this still isn't a for loop. It's not an array. It's not something that I can code up right away, right? So how do we get to this coding point? And here's a couple of approaches, a couple of rendering concepts that one way or another implement either subsets or the entire rendering equation or approximate it. Okay, and what I want to talk about now specifically is path tracing. I talked about path tracing already in computer graphics, so this is again sort of a repetition here. Okay, so path tracing is interesting because it's A, super simple, and B, it's a direct implementation of the rendering equation. Okay, so as a matter of fact, it was proposed in the same paper ages ago, like literally a couple of decades ago, in the same paper where the rendering equation was introduced to computer graphics. It also contained a solution, a numerical solution to the rendering equation, which happens to be what we call path tracing. Some folks today call this ray tracing, okay, which is not entirely wrong, as path tracing uses ray tracing at its core. I still like to keep this distinction alive because it makes a lot of sense to distinguish what I've previously introduced, weighted ray tracing, from path tracing, because they share a lot of the implementation, but they have substantial differences. Okay, so it seems like literature is moving towards ignoring the term path tracing more and more, but that actually leads to ambiguities that I'd like to resolve here. Okay, that said, let's look at ray tracing first. Okay, not path tracing. Let's look at, in particular, recursive weighted ray tracing. That's basically what I introduced before. This idea, we've got an eye. From this eye, through each pixel, we shoot a ray. That ray potentially hits part of the scene. And when it hits an object, at that object, we compute a couple of rays. We compute a reflection ray and repeat the process. We compute a refraction ray and repeat the process. And we compute potentially a ton of light rays that all just check whether there's something in between the light source and the surface point. But those, and that's an important part, in particular why I omit them here, is those do not spawn a recursive computation, right? So the light rays just check, do a simple trace to the light source. Is there something in the way? Whereas reflection and refraction, they cause a recursive call. Okay, and what you can see here is, let's just assume for simplicity's sake that every object in our scene combines the reflected and refracted part 50-50. Okay, so half of the final color of our object 1 here is from the reflection, so it's kind of a semi-translucent object that reflects half of the scene and refracts half of the scene. It doesn't have a color on its own. Okay, so if we do this computation and we just kind of do a trace in our code, what we would do is we would shoot our first ray at the object, we'll shoot the light rays, we'll ignore them here, and then we cast these two rays, the reflection and refraction ray, and then we simply repeat the process. Okay, let's focus on the one at the top. So that again might hit an object. That again has a 50-50 combination. So now this here contributes 50%. If we ever find this value here, or this value here, those two contribute 50% to the overall value, which is then the value that the pixel gets. Now, if we repeat this process with reflection and refraction, we get now 4 objects potentially. And those contribute, well, 25% to the final result. And then we get 8 objects, and those contribute, well, 12.5%. Okay? And this continues as long as we let it continue. Okay, so, and there's an interesting thing to notice about this way of computing an image. And that is, well, the complexity grows exponentially, which is always bad. Okay, exponential growth is pretty much the worst thing you can produce. Okay, so that's bad. But there's a second observation that makes this even worse. The more computational levels we introduce, the less we gain. Okay, so we start with 100%, we do twice the work for 50%, 4 times the work for 24%, 8 times the work for, and so on and so forth. So the more levels we introduce, the more we have to do rapidly more, but we rapidly gain less insight. Okay, so that's never a good idea. If you do more and more work and you gain less and less for that, you should probably stop doing it. Okay? And that's kind of another way of thinking about path tracing. So let's get rid of this tree thing and let's replace it by a path. Okay, so we're literally following a path. Okay, so how does that work? And what does all of that have to do with the rendering equation? Okay, so let's quickly recapture ray tracing, weighted ray tracing, using another depiction, another visualization here. Again, we've got our eye point, our eye, we've got our viewing ray that hits the surface, we compute the normal, we compute the reflected, the refracted or transmitted ray, and we compute this light ray. Okay, so and then this process continues, we hit something, we continue here, and so on and so forth. Okay, so first of all, that has this immense performance issue that I mentioned before. And second of all, there's another gigantic problem here, and that is, like, this ignores pretty much everything, right? It ignores all direction except for, well, those two here, right? So, and maybe the light direction. Well, let's say 3. But there's still infinitely many that we don't consider. What happens with light that comes from here and happens to get reflected into that direction? Well, we ignore it. What happens with light from here that gets reflected in that direction? We ignore it. Here, ignore it. Here. So we pick, you could argue that this way of computing, it picks pretty much sort of at random 2 direction and says, okay, that's what it looks like, right? And this results in this problem that we can only handle like perfect mirror, perfect transmissive object, or things that where we just compute local lighting as we would do in, well, just simple, straightforward rasterization. So wouldn't it be better if we have this situation here and we're interested in the color of, say, that point here, and for that we need to compute the radiance, and for that we need to gather all the incoming ranges, if we would just look at all directions. And as a matter of fact, that would be significantly better. However, that would take quite a long time because it's an infinite amount of directions, right? So that's bad. Okay, but that's not all. Okay, because, well, what happens to those rays, right? Let's look at some of those rays. At those rays, again, we would have to look at infinitely many directions. So we now have an exponential function where it's not 2 to the power of depth, but it's infinity to the power of depth. And that doesn't really improve things a lot, except that the quality would probably be better if after an infinite time to some exponent, we would not get a result. Okay, so you get the idea. Conceptually nice, practically entirely worthless. Okay, so let's now look at what path tracing does, which is a completely nutty idea, but it actually works. So that's kind of a funny thing. Okay, so the idea is, instead of looking at all directions, as I've said here, or instead of picking 2 like pretty much arbitrary directions, we can just pick any arbitrary direction. Okay, so the idea is, we look at a surface point, like we've got our incident ray here that hits a surface point, and we literally pick a random direction. Could be this here, could be that here, might be this here, and then if we happen to hit an object, we'll again pick a random direction. Let's say for some, I don't know, for whatever sake, I happen to pick this direction here. Wow, I hit another surface. And let's say I happen to pick this direction here, and wow, cool, I hit a light source. So if I hit a light source, I finally gather something. So I'm assuming that anything else here doesn't glow. Okay? So the basic idea of path tracing is to follow a path. Notice that this white thing is now a path. It doesn't fan open, right? We hit a surface, we pick a random direction, and either that random direction leads us to nothing, like literally background, we'll terminate that, right? It leads us to an object, so we hit an object, then we just pick another random direction at that surface and follow it. And that can be transmissive or reflective, whatever. And we continue this process until, well, we leave the surface, or by some crazy, incredibly unlikely coincidence, we happen to hit the light source. If we hit the light source, we say, oh, cool, light, and we return this value. Okay. So now you might say, well, that's a stupid idea, right? I mean, what will I get out when I run this tool? Like, what if I shoot a ray on a surface hit, I pick a random direction, and I check what I see in that direction? Don't I get random? Well, sort of yes, but then again, this is exactly how I computed this image here. Well, except for one tiny detail that I omitted. So let's first look at this image here. So this is actually the image that I got when I ran this computation. So what do you see? You see randomness, or also referred to as noise, which is, I suppose, no surprise. I mean, we've got a completely random approach here, so we get a, well, not completely random result, as it turns out. okay? Because we're actually sometimes lucky that we hit the admittedly somewhat enlarged light source at the top, right? For starters, any ray that hits the light source directly, of course, terminates, right? So we get a pretty good image of the light source. So that's perfect. And then for those surfaces that were somewhat glossy, I also happened to get a reasonable result. And anything else was sort of noisy. Well, how do I get this noise out? How do I get to this point here, which I suppose looks a little bit better or more realistic than this one? Well, you do what you always do if you have a randomized approach, or what you often do when you have a randomized approach. You repeat the process, okay? So you compute this image again. You get another result. It's got noise in it, and hopefully different noise if you have a reasonable random number generator. And generating random numbers is a really, really hard thing. You can refer to my data structures and algorithm class on a couple of issues with the random number generators. But nonetheless, let's just say it's a big deal, but we leave the theory here to another day. So I'll just repeat the process. And then I repeat it again, and then I repeat it again. And here's the hope. Here's this law of large numbers. That is, if I just repeat a random process often enough, it will converge to the expected value. The expected value is, in this case, the image. So if I take this here and repeat it, and at the bottom you can actually see I start from 1 try to 30,000 tries. And if I just repeat the process, and then always average out over the images, after a while you don't see any difference. So I give you a zoom in on the center that I've broken on top left. You see that with an increasing number of retries and averages over all of these, I converge actually pretty, well, it's not super quick, but I'm pretty much converged at this point, right? I let it run to 30,000. And if you look very closely, which is probably not visible in the Twitch stream because it got compressed out by the codec, but nonetheless, you see that it converges to that result, okay? So if you want to play around with it, it's actually not a very complicated piece of software. So if you want to regenerate that image here, you go to that URL. So there's a guy called Kevin Basin who implemented a small path tracer, hence small PT, and that's what I used to compute this image here. Small because it's only 99 or it's 100, I don't know, it's either 99 or 100 lines of C code. And those 100 lines include the scene itself, include the reader for the scene, include the whole geometry. It's even object oriented and not just throwing everything in one line. So no line is longer than 80 characters. So long story short, it's actually a pretty simple thing to do. It's not very efficient though. It takes forever to compute this, but nonetheless, it's pretty simple. I've also done a series on my late night coding stream where that image comes from, with a little bit more sophisticated or presenting or implementing a somewhat more sophisticated path tracer. So if you're interested in all those details, some of what we will do here also in the exercise later on. But if you're interested in all the details, you can go to that YouTube playlist. It's embedded in the PDF as well, so you don't have to copy that YouTube playlist and watch it. It took a few sessions to explain the whole thing, and that is based on a work of my colleague that is called ray tracing on a weekend. Okay, so his name is Pete Shirley. His idea is that you can teach someone to do this here, to do ray tracing, and he actually apologizes in the first sentence about calling this ray tracing because it's actually path tracing. But nonetheless, it should be called path tracing on a weekend. Okay, the book is open source. You can also download that. So it's a pretty simple approach, and it can generate relatively lifelike images, right? So here in this image, we've actually included things such as depth of field. So there's a lens model. Notice how the spheres in the back are blurrier than the one in the front, and you see different types of materials. So again, you've got a mirror material, you've got a a glassy material, you've got a glossy material, all kinds of things. So the bottom line is it's pretty straightforward. And it's based on this idea, okay, let's just shoot a random ray. You can be a little bit more clever about the whole random ray thing. And I explained this in some details in computer graphics. You might remember the concept of importance sampling, right? Instead of just choosing the direction at complete random, you can actually have a non-uniform distribution, right? So you can For instance, for a diffuse surface, such as this one here, that's a purely diffuse or Lambertian surface. For a Lambertian surface, it doesn't really make sense to do this at complete random, but you want to you want your distribution to be cosine distributed. That means you want to statistically shoot more rays upward and fewer rays in the peripheral region. Why? Not because you expect more radiance from upwards, but if radiance comes from the top, it is more important because everything that comes is multiplied by this cosine term. Since it's multiplied by this cosine term, you might as well shoot 10 times more rays at the top than to the sides. Or, to be absolutely precise, shoot cosine more rays to the top than to the sides, and then you don't even need to weight things anymore. So, long story short, that's a path tracer. Path tracer, very simple thing, very powerful, is a direct approximation, or it's a direct implementation. I mean, convergence towards the result of the random equation. Why does it? Well, because of this idea of repeating this process and then computing the average, which is literally summing up things and dividing by the number, which is exactly what an integral does. Okay, so this is like a one-on-one implementation of the rendering equation, and it's simple. The only drawback it's dead slow. Okay. What can you do to make it faster? Well, do fewer repetitions. If you do this, you get more noise. So if you actually look closely at this image here, so it still has some noise in it. What can you do against noise? Well, again, more iterations, and that's a very popular idea pretty recently, is you filter your image. Like you blur your entire screen, and then the noise is gone. Well, everything gets blurrier in the process. But if you do this blurring process very smart, then this is maybe not that obvious. Okay, and this is, for instance, what modern game engines do when they say we add ray tracing to our game. So what they do is they do path tracing to start with. So they do path tracing, but only very few iterations, which can still be executed fast. And then these very few iterations, they just get blurred with a very smart blurring kernel, which is then usually based on some AI learned filter bank. Okay, so where you try not to filter across edges and so on and so forth. So that's kind of the state of the art for ray tracing in games, is literally do path tracing and then post filter to get rid of the noise. So cheat in essence. Like if you post filter, you cheat. Okay, so. But I guess you gathered that concept by now, that cheating is actually a good thing as long as you know that you're cheating, right? There's a difference between cheating in an exam and cheating in graphics. Okay, so that's path tracing. And that is concept number one, to get this global illumination, get this physics-based lighting to work. Things to remember: path tracing, simple to implement, damned hard to even get remotely fast, and pretty much impossible with current hardware to get to interactive rates for reasonable scenes. Okay, so there's sometimes images that you see, well, we do path tracing here at interactive rates. So for instance, for this scene here, if you implement this really efficiently, even on a CPU, you get it to interactive rates. Okay, so this here maybe took a few minutes, I think 15 minutes or so to compute, but this is just because it's straightforward and not optimized. If you optimize the hell out of it, you can render such a scene on a CPU interactively. You can, of course, do this on a graphics card with the hardware support interactively, but that's not a reasonable scene because it's super simple. It just contains spheres. As a matter of fact, even the floor is a sphere. It's just a big one. So for a reasonable scene with complex geometry, with changing objects, interactions, it's hard. If not, at least for now, it's out of reach for interactivity. So we cheat. Okay, so that's path tracing. What I want to do now and for the next couple of streams is I want to introduce, well, approximations or hacks, whatever you want to call it, approximate methods that sort of deviate from this, like, can do the entire rendering equation thing, path tracing, to, well, okay, let's say we can't do object type X or light type Y, okay? But all the others we get perfectly right. Okay, so in that case, the result is not wrong, it's just restricted in a sense that in this scene we can't have a mirror. It wouldn't work. Or I have to cheat if I want to introduce a mirror. Okay, but if the scene doesn't contain a mirror, we can do it, and it's going to be, well, 1,000 times faster. So for any scene that doesn't have mirrors in it, you're good to go. Okay, so and that's pretty much the idea of the next couple of streams, or the next couple of topics, that I'll do some simplifying assumptions about the scene. So I make some restriction and present you a method that will work for those situations. And that actually is a much more a reasonable approach than what we took before, where we would just approach from, okay, what can we do in a millisecond? Okay, now we approach this. Okay, let's say if I ignore that type of geometry, if I ignore that type of object, what can I do correct? And maybe then it works in a millisecond. Okay, this gives you much more control over the quality. Okay, and the first method I want to talk about is radiosity. Okay, so radiosity, you've already heard the term radiosity. It's a quantity, and it's not just a quantity, it's also a rendering approach which makes heavy use of that quantity. Before I start with radiosity today, time for questions. So are there any questions? Well, I guess the sound works. At least that's the thing. Okay, so I assume none. Good, then let's look at what radiosity does. Radiosity is built on radiosity, which in turn is built on irradiance. Let me just repeat the irradiance. That was one of the three quantities, radiance, irradiance, radiosity, that I said you should not forget. Which is okay if you forgot them today. You have time to recapture them and memorize them. Okay, radiance, irradiance was the thing, watts per square meter. Okay, what was joules per second? So the whole thing is joules per second per square meter. So it's like how much energy is emitted or received over time over area. Notice that I've ignored this whole C radiant thing here. That was kind of weird anyhow, right? So let's ignore that. If I ignore that, if I don't do a per direction term, what this means is I can't talk about directions anymore, right? All that I do is always into all directions, right? It's just as if when I would talk about joules, I'm not talking about time anymore. So what I would get is the total energy, okay? And here I get also the total energy, but over all directions, or the total flux over all directions. So what this sort of simplifying assumption means, if I simplify to watt per meter squared, or again, what is joules per second per meter squared, is that whatever the result will be of my computation, if I let this computation be based on irradiance, I lose a direction dependence. Okay, like what does it mean that I lose a direction dependence? I mean, we're doing computer graphics here. What does this mean graphically? Well, it literally means that whatever I'll deal with must have a direction independent reflectance property. Okay, and then I can use radiosity, which was just scaled irradiance. That's the radiosity equation, the first radiosity equation. And what does that mean? This I lose direction dependence. It means this thing will only be able to handle diffuse surfaces. Okay, no specular surface, no brushed metal, no polished metal, no mirror, no glass, no, I don't know, car paint, right? Just a car with foils on top of them, which are pretty cool these days anyhow. So I restrict myself apparently to diffuse surfaces. Now you might say, well, that's a bummer, right? I mean, I want these cool shiny surfaces. I'm a big fan of chrome and leather and lace and whatever. Well, the thing is, what was hard before? Like let's recapture weighted ray tracing. Didn't I say, well, we're just in weighted ray tracing, we kind of arbitrarily pick a reflectance and refractance direction. And that I said was a pretty dumb idea, except, well, if your surface is a mirror, or if it's a piece of metal, shiny metal. So the thing is that restriction to diffuse surfaces helped us tremendously here, as we'll see when I run through some of the mathematics involved in radiosity. But the cool thing is it handles all those tricky surfaces, right? The diffuse surfaces aren't the one that are, well, boring. Well, they might be boring, but those are the ones that are hard to compute, because those are the one where I have to look into all directions the same, where I cannot just say, well, the reflectance direction is what I'm curious about, right? So, and the idea with the radiosity is that we start with this thing, and then if we want to get a mirror in there, we can just compute it separately. It's not perfectly accurate then, because the two things have interdependencies, but nonetheless, getting a mirror in there is relatively straightforward, right? I mean, the easiest way is just use the concept that I've introduced before for a planar mirror, just copy the scene to the other side. Well, and then the mirror is gone. So this restriction, and that's a big deal. That's a big deal that we will see over and over in the next couple of streams. We often restrict ourselves to diffuse only surfaces. And that's a big restriction, but it's a restriction, we restrict ourselves to the complicated things. The easy things we can render on top of them. Okay, so you see radiosity, and that's a simplified version of this rendering equation. Okay, so here's again the rendering equation. I should not forget that. And here's again the underlying graphics for that idea, right? The idea was we gather those red components from all over the place, right? We add that to the blue component, that's the illumination of the thing itself, and then we check how much of that makes it into the yellow direction. Okay, so adding up all those components, and that's the integral here. And then inside the integral, we do this weighting factor, which is this crazy BRDF, right? And I've just introduced that one way of dealing with this is to use Monte Carlo techniques, which is just a fancy, like impress folks at a party like term for, let's just throw in some randomness and repeat the concept so often that the randomness goes back out. Okay, so well, ray tracing and path tracing, or the ray tracing that a lot of people mean when they the path tracing that a lot of people mean when they say ray tracing, is a so-called Monte Carlo technique. Okay, I mean, there's a little bit more detail to Monte Carlo techniques, but the bottom line is just put in some randomness, repeat the process. Okay, so that's approach one. Approach two would be something that's called photon mapping. I'm not going to talk about photon mapping here. It's a nice hacky method that unfortunately is biased, meaning it doesn't converge to the correct result regardless of how long you execute it, but it's been popular for a while because it generates also some somewhat high quality images that are unfortunately biased and still take a while. But it's a worthwhile technique. So if you're interested in knowing how photon mapping works, just read it up in the book. We can point you to literature if you're interested, or you can just search it on the web. The idea is pretty straightforward. So you basically, you shoot rays from the light source, and you shoot rays from the viewer, and then sort of where they meet, in a sense, this is where you do some computation. But anyways, photon mapping is not what I want to talk here about. I want to take the third route, and that is radiosity. So here's a typical radiosity scene. Why can I tell that it's a radiosity scene? First of all, it's got all the nastinesses that other systems are suffering. One is it's got area light sources, right? We have big light sources. We got these light sources here at the top. So they're big cubic light sources, right? We've got the big spherical light source here, and we got the big light source here. And remember, what did I say about light sources? What did I say about Uber light? Well, if you have an area light source and you run something like a shadow volume, or you run a ray tracer, right? You end up with having to follow a ton of rays, having to repeat the computation over and over again by simply sampling a surface, right? One of the cool things about radiosity is that it actually doesn't care how big a light source is. It has absolutely no impact whatsoever how big a light source is on the basic computation. So since it has no impact, we'll use it, right? We'll use it where it is, wherever we need it. As a matter of fact, it actually converges faster when the light sources are bigger, but computationally, it doesn't have an impact just for the numerics. It makes a difference. So big light sources is one thing where you can check that that's obviously being computed by radiosity. And the other thing is it's all diffuse surfaces. Okay, here's another example. So that's a somewhat less artificial scene. Okay, so this looks a little bit more realistic, even though I guess you could still tell it's a computer graphic image. But I think it actually gets the mood across pretty well. Again, gigantic light sources, almost the entire ceiling is a light source. I mean, it's broken down into lamps, but it's still a lot of illumination coming from everywhere. We got large windows that are light sources. We got large lamps that illuminate the pieces of art here. And everything is diffuse. Okay, so that's an easy way of telling that someone is like showing off with radiosity and showing all those nice effects that a ray tracer has a hard time handling. So here's again a comparison of the same scene now when I compute it with a weighted ray tracer and I try to sample an area light source. So I shoot a ton of rays to sort of get this umbra penumbra, so the soft shadow thing done here. It still looks sort of a lot inferior than this radiosity image where I get all these cool like secondary effects, right? I got this yellow ball that bleeds its yellow color on the ground. It's just like the blue ball here and the red ball. So you get all these cool effects. And that's just hard to do with straightforward ray tracing. And path tracing handles that. Okay, now I've claimed that radiosity is this cool thing. So how does it work? So we should probably get to that point soon. So how does it work? It makes two simplifying assumptions. Okay, one is we only have diffuse surface. I mentioned that already, and it makes a second simplifying assumption over the rendering equation, and that is the scene is discretized. What does this mean? Well, it means that the scene is made up of elements that have a finite size. And I would say, well, isn't this always the case? Well, we build our scenes of triangles or whatever. Yeah, it's usually the case. So I would say that the second restriction, that everything has to be set up into what is generally referred to as a patch in radiosity, is no big deal. But conceptually, it is a big deal because the rendering equation is an integral, it's a differential equation, right? It deals with infinitesimal points, it deals with directions, so it can handle everything. Radiosity assumes that the scene is made up of a number of things. So it can be a million things, but it can't be an infinite amount of things. Okay, so you have a finite amount of objects. Could be triangles, could be quadrilaterals, could be spheres, whatever, right? As long as it's finite. Okay. Good. Those are two restrictions: finite number of objects and or components. An object can also be a triangle, right? Components and just diffuse illumination or diffuse reflection. Okay, so now let's get to the basics. At the top, you see the rendering equation. Okay, so I've made it. I've now drawn it in one color, but it's still the same thing, right? It's still blue, white, red, okay, and the left is yellow. So I just figured we're at this age where we can handle black and white. It doesn't have to be colorful. Okay, so what I now want to do is I want to take this rendering equation from the top and I want to gradually change things by introducing those two restrictions, right? Finite number of objects and just diffuse reflection, to change it to another equation, which is then curiously called the radiosity equation. And then once we solve that, we'll have our method called radiosity. Okay, so let's first deal with this finite things restriction. Okay, and since when I break my scene down into a finite number of objects, of components, of patches, let's stick with patches. Okay, so we break the scene down into a finite number of patches. Then look at what I do here at the top. Right at the top of this equation, I do an integration over all directions. Now, if my scene is made up of a finite number of patches, I don't have to take care of all directions. I could just say, well, for one patch, just look at all the other patches, which is the same as all the other directions, because where there's no patch, there simply isn't anything. Okay, so we'll basically reformulate this integral from directions to patches. Okay, so this is what you got here. So you got one patch, and I've just drawn this as a quadrilateral, but it can be pretty much anything, right? You've got one patch, and then we got another patch. And what I want to do in the end, I want to iterate, and again, an integral is just nothing but an iteration over, well, admittedly, an infinite number of things. I want to iterate not over directions, I want to iterate over patches. And now I want to know what happens between two patches. Like, how do they exchange energy? Okay, let's look at these two patches. What do I know about them? Well, I know hopefully where they are. Okay, let's just say I quantify them by their position and their orientation. Okay, let's just assume that each of those patches is relatively small. Okay, it's a finite number, but it's still small. And I want this to be planar. I want this to be flat. So it's quantified enough by its normal vector. So what I then get is I get a point here and I get a normal. So that point is sitting on a surface with a normal. And I get another surface and that also has a normal. And let's just, at this point here, keep things a little bit more general and say, well, these pitches can also be pretty small. So I just call the area dA, okay, differential area. So technically at this point, I allow them to vanish to a single point, or I look at the limit to a single point, but we'll later on make that finite. But if I do this, how do these two pitches see each other? Like if they emit energy, okay, one thing that's immensely important is how much of their surface do they see? So if I have two pitches and they're oriented this way, then they see each other pretty well, right? Now I take the surfaces and take them apart. Well, they still see each other pretty well, but they get smaller and smaller, right? I mean, when they're further away, their influence decreases, not because energy is lost, but simply because they cover a smaller area of the hemisphere. Right, so it's not like energy is lost here. We're still assuming vacuum in between, but they simply get smaller. So distance between the 2 points matters. How does it matter? Well, it increases the size in x and in y, so it matters quadratic. So if I increase the distance by 10, it shrinks by 100 the influence. Okay, so that's one thing. So the further I pull them apart, the smaller their influence to each other is. The next thing is, like, what happens if I start to tilt one of these patches, right? Up to this point where it's 90 degrees. Well, then nothing is exchanged, right? So this thing doesn't glow perpendicular like this point. It just kind of emits energy here. And this one doesn't receive. Now, if I kind of tilt this situation, I again get 0. Or if I do it this way, I again get 0, right? So what matters is the relative angle of the two normals to each other. Okay? If they're both facing the same direction, cool. If they're at 90 degrees angle, not cool. Okay, like, do we know a function that has this property? If the angle is 0, it's high, and if it's 90 degrees, it's 0. Yeah, that's the cosine. And in between, the cosine happens to compute exactly the area facing the two. Okay, so this is this function here at the bottom, which kind of looks scary, but as it just tells me, it's like, okay, instead of looking at this differential angle, okay, this some direction, if I integrate over all directions, I can also look at the differential area times this weighting term, this cosine weighting term, which is nothing but the angles between the two normals, divided by the distance, okay? And this is just y minus x squared, okay? So, and I can reformulate this if I want to. I can solve this for dA. Okay, so this might look a little bit tricky, and it actually gets worse in the next couple of minutes. But what I want you to remember, okay, so I know that this can throw some students off because I start to use 10th, 11th grade mathematics. But nonetheless, what I want you to remember is the overall idea, right? I mean, at some point I want you to understand the formula as well. But for start, I want you to remember the basic idea. The basic idea is we look at patches and how do these patches influence each other. And that's supposed to sort of make sense right away. Good. Now, if I take this thing here, okay, and since that is, that's a scary thing, okay, we call this G, okay. So this is really, this term here, we just call this G, or the term with which we weight omega, we call this G. And notice that since we have two angles facing each other, this here is basically the connecting distance to one angle times the connecting vector to the other angle. That's like the total angle between the two. Okay, so since this is a little bit scary, it involves cosines and it involves norms and squared. Well, it's just a distance, but whatever. Okay, so we call this G. Why G is a geometric term, okay, because this depends on the geometry. Okay, so and then we'll just put this aside and say a geometric term, never think about it again, scary thing. It just depends on the geometry. Okay, cool. Now let's introduce a second term, that's the V term, which stands for visibility. Now what might happen is that we did all this fancy computation with these two patches each other and whether they face each other or not. But then unfortunately there's something in between, like my head. Okay, so if my head is in between the two patches, regardless of how cool they're aligned to each other, they simply don't see each other, so they don't directly exchange energy. Okay, so we'll just introduce a pretty simple term that says 0 if they don't see each other, and 1 if they see each other. Okay, so that might be tricky to compute, to figure out if there's something in between, but let's forget the computation for a second. We're at this theoretical level here. Okay, so we'll just introduce this term we, and somehow we'll figure out if two things see each other. Okay, and technically it doesn't have to be 0, 1. You could also introduce things later on. If the differential patches actually have a certain size, you could also see, well, they see each other 50%, right? So, but for differential patches, only a binary metric makes sense. Now with this V and G, we can actually replace the radiance term in the top one. The radiance times the area foreshortening term, right? So, or more specifically, well, the radiance needs to remain there, sorry. So we can replace the area foreshortening term with that one, okay? So, and we can change the radiance here. So what we get here is, see at the top, we say incoming radiance times area foreshortening, and the I in the radiance is very important. Okay, so the incoming radiance is whatever makes it to the patch, or almost to the patch, and then it's multiplied by this area foreshortening term. Okay, but that's not necessarily the radiance that was emitted. Why? Because, well, first of all, there might be an object in between. Okay, so that makes a big difference. And again, the radiance, like which radiance are you talking about? The one that was emitted this way or that way or that way? Okay, so we want to get this direction out later on. Okay, so I say, okay, well, the radiance that was emitted times the visibility times this G term, this is what ultimately arrives at a patch. Okay, and now notice, since I introduced this per area here, now my integration is over all surfaces instead of over all directions. Okay, so there's some few tiny changes, but the bottom line is, between these two equations, I actually so far haven't made a real reduction in expressibility. So I've just changed the way how I see things. Okay, at this point, when I'm still at the dA level, it's still a differentially small patch. When it's differentially small, I still have an infinite integral over an infinite amount of patches. What we'll later on do is we'll make this finite, and we'll make a sum. We'll introduce a sum here. Okay. Now, if I make this finite, then my scene will look somewhat like that here. Okay, so I now took a scene with a window, a table, a light source, and I've broken it down into a finite number of patches. As you can see here, some patches are triangular, some are quadrilateral. Right, so there might be other patches that are too small to see other polygons, whatever. But the bottom line is, yeah, I can break this down into a finite number of patches and then adjust my equation from before, adjust the radiosity equation. It's actually way harder to adjust the rendering equation to that than the radiosity equation, because the rendering equation doesn't have this notion of a finite patch or whatever, right? I mean, I could integrate over finite bundles of rays, right? I could like make the solid angle finite. That's what I could do, but this kind of finite angle would be different for each patch, right? That's kind of awkward. And that's what the radiosity equation solves. Okay, so now there's one quirk, and that is when I do this computation later on, what I will get out is one value per patch. So since I do the computation per patch, I will get out one value per patch. I'll basically get one radiosity value per patch. This means that at least in the first approximation, every patch will have a constant radiosity, and consequently it'll have a constant brightness. So we'll see these blocks. The result will be blocky. Now you could say, well, I'll just make those blocks so small that you don't see it. But here's the catch. That is, well, if some of those blocks end up having the same radiosity, we could actually replace them by a big block. But if we have a change in radiosity, say because maybe there's a shadow, the visibility changes, and that means we have a shadow here, then we would need more. And that's unfortunately an implicit problem, right? We need to know the radiosity distribution to figure out the patch distribution. And we need the patches to compute the radiosity distribution. So that is not cool. And that's one of the issues with the radiosity. How can you fix that just as a kind of look ahead idea here? Well, you try to make your patches smaller when you're close to something else, because then, for instance, visibility might differ from point to point. So here you can see a scene on the left as it's rendered, and on the right you can see how it's been broken down to patches. You see bigger patches here and smaller patches wherever I'm close to something. Okay, but that was just kind of a look ahead. So let's continue with the actual simplification of this rendering equation, where I replaced the integration over directions, where I replaced that one by integration over, at that point, infinitesimal small patches. Let's introduce this I only want diffuse reflection term. Okay, remember we have the radiosity equation here. So that's, by the way, another radiosity equation. So there's actually two. So this is one, but they're closely related. They're actually a reformulation of the same thing. So that's why we call them both the radiosity equations. But nonetheless, that's the one that I presented before. And as you can see, this one doesn't have a BRDF, and it just has this factor rho in it. And rho is apparently the ratio between the radiosity and the irradiance. I mean, that's quite obvious from this part here, right? If I just take these two things and, well, divided by the irradiance, it says rho is B divided by E, done. Okay, so it's no rocket science here. And now let's get to this point where we try to figure out what the hell rho is. Right? I mean, I said if we have a diffuse surface, then the BRDF is constant, which is not really correct. That was just an intuition. Why is it not constant? Well, what's more precise is to say, if I have a diffuse surface, then regardless of what my reflectance direction is, I will always get the same amount of radiance. Okay, meaning that if I have a diffuse surface like this wall here, which you can see, so if I change, it's just a simple white painted wall. So if I change my position, it'll look the same. Okay, and that's actually a pretty normal thing. So we have a lot of objects around that are diffuse in nature. But remember that BRDF thing didn't only contain this ratio between the two radiances. It contained the derivative thereof. Well, if it's constant, the derivative is zero. But the other issue is that it contained this cosine term in there, unfortunately. So it was divided by radiance times cosine. So even if the ratio is constant, still the BRDF isn't constant. So we can't just simply say, oh, the BRDF is constant, let's pull this in front. That doesn't work. So we have to first split this up into this cosine part, L, and the non-cosine part. Okay, so that's what I do here. Okay, so I have this integral here at the top, where I have this cosine part, that's the cosine multiplication, and then I have this diffuse radiance, right? So this is the reflected radiance that I get. And that is constant, and that's somehow computed as a ratio of the incoming radiance, but let's just say I know this reflected radiance right away. Okay, so that I can pull in front. Okay, no doubt about that. But unfortunately, there's this product with the cosine term in there in the BRDF. So what I need to figure out is what is the integral over all cosines, so to say. Okay, and I integrate here over omega plus. I've never really introduced omega plus. I should probably do this. This is the hemisphere. Okay, so omega plus means the positive part of the hemisphere. And if you want to look at the other part, well, you just have to double that result, right? But since we're not caring about translucency here, so we don't care about the stuff that happens, the light that comes from below the surface, we can just integrate over the upper hemisphere. So all we have to do is compute that integral here. And that's a somewhat nasty integral because it's over a sphere. I mean, when was the last time that you computed an integral over a sphere? So let's simplify things here a little bit, or make them more intuitive. And that is, well, instead of saying I integrate over the sphere, I mean, what does it mean to integrate over a sphere or a hemisphere? It's like, well, we take a bunch of angles in one direction and we take a bunch of angles in the other direction and we take all combinations thereof. Okay, so I'll basically do one integral over from 0 to 2 pi, which is a full circle. Okay, and then from 0 to half pi, which is a quarter circle. Okay, so I take kind of in all direction, I take these quarter circles, which in sum makes up a hemisphere. Okay, so then you can do the math, and I save you that part here. So what is the cosine that I get? Well, the cosine is the cosine for all of those directions is a cosine that depends on it's a cosine times sine. So, and that is, you can actually see this here at the top, because the radius, the higher or lower I get, that's actually the sine. So that changes the radius of the one angle that I do 360. So I basically get this product of a sine and a cosine if I break this up into those two angles. Okay, now when I do this, I can start to simplify things a little bit. Okay, so what I can do is I can simply run a bunch of trigonometric rules on top of that, and what I will get is that this is simply 1/2 times sine 2 times the angle pi here, phi here, or sorry, it's theta, it's not phi, it's the angle theta here. Okay, and then if I look at that closely, well, it doesn't depend, sorry, I just compute this integral here. So that's an integral from 0 to 2 pi. So I basically plug in 0. So I compute the integral first, then in this undetermined integral, I plug in the 0 and I plug in the 2 times pi. That's what I did here. I actually computed this integral, which is minus 1/2 times cosine theta squared. Then if I plug in 0 in this one here, this here becomes 1. It's 1 squared. If I plug in half pi, I also get some value which happens to be, let's say, cosine of half pi squared. What is that again? Maybe something inherently simple. Isn't that 0? Let's see. Oh, sorry, that's let's see, that is what is cosine half pi? So that's also something that you can figure out. Maybe someone can help me out here. But is it? No, it's not 1. I think this is well, just figure it out. I can't remember. Anyone look this up for me? It's something that makes sense. Something that's not like any rational number or whatever. You get something reasonable out. I think you get 0 out. Or oh yeah, 0, right? Okay, thanks. Yeah, I mean that one makes a lot of sense. Yeah, so you get 0 out. Okay. Okay, yeah, that will make sense, because then yeah, that makes a lot of sense, because that would give me the result that I'm looking for. Yeah, so I get 0 out for this one. For 0 I get 1. So I basically get 1 times 0.5, or more specifically 0 times 0.5 minus 1 times minus 0.5, which happens to be 0.5. Now I compute the integral from 2 pi to pi over 0.5, which happens to be pi, right? I mean, this is simply 0.5 times 2 times pi, which is pi. Okay, so yeah, the only thing that I should probably remember is what cosine of half pi is, which yeah, it makes perfect sense. So sure, I mean half pi is 90 degrees. Yeah, dumb. Okay. Anyways, so bottom line is, okay, so this here evaluates to simply 1/2. The integral over a constant is simply the length of the integral times the constant. So bottom line is, this here at the very top, the integral over all those cosines over all direction is simply pi, which I guess is no super big surprise that if you look at terms over a sphere, that you get some pi-ish result. Shouldn't be a big deal. But what all this computation tells you is basically that if you have a BRDF that is constant, it's not constant, but that has a constant diffuse component, that has a constant weight, a constant ratio between incoming and outgoing, you can pull that in front, but you have to multiply this with pi. Okay, so because the BRDF always contains this cosine part, and that evaluates, after that computation, evaluates to a pi. Okay, so rho, and that's kind of the take-home message, rho is simply this diffuse component, so this ratio of the incoming and outgoing times the times pi. And if I multiply this with irradiance, I get radiosity. Okay, so rho is diffuse. Rho is diffuse reflectivity times pi, or in other words, the diffuse reflectivity is rho divided by pi. I mean, whatever you prefer here. Why did I do all that fancy computation? To be able to integrate this constraint that everything is diffuse into the equation here. So I basically take the BRDF, that's crazy anyhow. I take that out. Then I reintroduce another term here, which is this rho of x divided by pi thing. Okay. And then I cannot call this radiance anymore, but I have to call it radiosity because it's now considering all directions just the same. But I can then say, okay, well, the radiosity of a patch is its emitted radiosity. That doesn't change, right? I can still say, okay, well, whatever this thing emits, but now for all directions. So it's, again, not radiance anymore. Plus this weighting factor times the integral over the incoming radiosity, the visibility term, this geometry term times area. And then I have to do this for all infinitesimal areas. Okay, so that's, now we're getting to a point where we can talk about radiosities. Let's further dig into that equation. Okay, so let's quickly recapture what was this scary G again. It was this product of the two cosine terms, which ultimately is the orientation of the two pitches with respect to each other, divided by the distance. Okay, so now what else can I do? Well, I mean, I could argue that like v times g is a little bit, well, it's a little bit, it sounds so complex. Let's just take the product of the two v times g and call it g prime. Okay, that's the next step. Just that you know, when you see this g prime, or when you see v is gone, it's not gone. I just plug this in here. And the argument is, well, it's still a geometric term, right? Because the visibility has something to do with geometry. Okay, so we can still call it a geometric term. We just call it g prime now. And that makes this equation even shorter, right? I mean, we tend to just take all the complexity, pull it into a constant that is scene dependent, and it gets simpler and simpler. Now comes my next assumption, and that is, let's say all the patches are planar, okay? So that they're all made up of tiny spots. So what I can do is, instead of saying integrate over all surfaces, okay, as I did before, I could say, well, I mean, if those are planar surfaces made up of little spots, right? I can just integrate over all those spots, right? Instead of saying, okay, from this one patch to the other patch, I could say, well, let's just look at all combination of the one patch and the other patch, right? So, and then just sum them all up, okay? And that's what I do here. So I'll basically just do two integrals, right, over all of those points, right? So all of the points on one and the other patch. And then I need to normalize this by the area of the patch, okay? And then sum up over all possibilities, right? So sum up over all patches that are now made up of these infinitely small points, right? So the trick here is that I say, well, instead of having infinitely many patches that are super small, we say, okay, let's have a finite number of patches, but each patch is made up of an infinitely large amount of points. So you could argue that in summary, and that's in fact true, mathematically true, that the result is the same, whether I kind of quantize my infinitely many points into a few buckets and then sum over the buckets, or whether I sum up over this infinite stuff, is the same. Okay, and that's what I do here. So I sum up, this is now a finite thing, that's a sum over those buckets. I say 1,000 patches, and each patch is made up of, well, a lot of points. So infinitely many points. Now the next trick is, okay, well, this here again just depends on the geometry, really, right? I mean, this is just the geometric term integrated over all of those patches, right? So to make things simple, we'll just call this thing F, Fij. Okay, and it's dealing with two patches, I and j. So and then we get this very convenient equation here at the top, which looks super non-scary, that simply says the radiosity equals, for a patch I, equals its emitted radiosity times its reflectivity, so it's always it, because it's always patch I, times the sum over the radiosity over other patches, times the factor F here from I to j, from j to I, to get this right. Okay, No, it's I to j. Oh, okay, my bad here. So it's I to j. It's simply read from left to right. It's I to j. Okay, so this here can be read as, I mean, well, the whole complexity is in f, right? I mean, f is not this crazy big thingy here, right? But this here reads pretty simple. It says, I mean, how much, again, if we just ignore radiosity, irradiance, and radiance and all that stuff, okay? You could say, how much does a patch glow? Well, how much does it glow by itself? Plus, how much is it illuminated by other patches, multiplied by some factor f. We sum this all up and then say how much of that do we reflect. Okay, and this is actually almost intuitive, except for one super crazy property that this equation has, and that is it's completely upside down. Okay, no one noticed that actually. Like when I thought about this again a few years ago, well, a few decades ago actually, discussing this with colleagues, we noticed that Fij is the wrong direction. Okay, and I actually made a mistake just a few seconds ago pronouncing it the wrong direction. So Fij, I've actually written this down here. That's the fraction of energy that leaves an element I and directly arrives at element j. This directly is important because it computes all the interference in between, right? How much do they see each other? But the bottom line is this is the energy that's emitted from I and arrives at j. Okay, emitted from I arrives at j. What I do is, curiously, I multiply the energy of j with this factor. So if you literally pronounce this equation here, if you spell this out, and that's the fun part, it says the radiosity emitted at I is its own radiosity times some factor, whatever, plus whatever it receives times whatever if it would send in the other direction, how much would then make it? So this here is the wrong direction. And it turns out Fij does not equal Fji. Here's the equality. Fij times Aj equals Fji times Aj equals Fij times Ai. Why are they not the same? Because one is normalized. They're normalized by the area. Okay, so you normalize by the area. Since you do this with one area only, to get them equal, you need to multiply by the area. So bottom line, this is wrong. And it's actually very curious because it's still correct. I remember the first time I pointed this out to a colleague, back then I was already doing a PhD. I pointed this out in a script to a colleague, and we're like, oh, well, okay, so this description is maybe wrong. Okay, so maybe this is the typo, and it's supposed to say the energy that arrives from J to I. So, but we realized, no, it's not wrong. So we figured, okay, well, then the equation is probably wrong. So it's probably supposed to read Fji. And then we realized, oh, no, it's not wrong. Or the entire literature is wrong. So we actually went with another PhD student. We went to our colleagues, and they were all like, well, this must be wrong. No. And then after a while, we kind of just sort of gave up and realized that it seems like hardly anyone ever noticed this issue. So we just did the math. And it turns out this equation is perfectly correct. It's just not intuitive. Okay, so and here's just because I have this personal story, and so you guys don't get this wrong. Here's kind of why this is not intuitive. And this is not intuitive because the thing that we're actually computing is not intuitive. And that is, you can actually see this when you work with the radiosity. I mean, in the end, you need to produce a brightness on screen. Okay, and the brightness on screen, let's just assume we're not doing colors here for now, is not the brightness of a patch. It's not BI, it's not a radiosity, but it's radiosity times its size, right? I mean, if a patch is bigger, it's obviously creating more brightness on screen, or it's generally emitting more, right? Radiosity is still is energy still per second per patch size, right? Per square meter. So to get the real thing, you actually need to do this here. Okay, so BI times AI. That's what you're really interested in. Okay, but usually no one accounts for this because, well, I mean, AI is something that you know. So BI is the quantity that's a real big deal. Okay. So all you have to do is, if you want to know exactly how much energy per time is emitted, you just multiply it by the area. Okay. So this is why hardly anyone considers this. But let's do it. And then it gets curious. So if I take this equation from before and I multiply this by its area, of course I have to do this both sides. So let's do it. I multiply this here by AI and here as well by AI. So since this is a sum, I mean, this is obviously, we obviously got a plus here, and that's also a fancy version of a plus. So we'll just multiply everything with AI. So we get BI emitted times AI plus rho times AI. So here's just our AI. So now it gets fancy, because what we know is that we know this FAI, FAJ, and I saved myself the AIJ. So we know that this equality holds here. Okay, so I can now replace Fij times AI by Fji times Aj, right? Because these two are the same. And now you see why that makes sense. Because of course I also need to multiply the incoming radiosity by the incoming patch size. But I've ignored that. I've factored this out here. And since I factored this out, I happen to be forced to either divide by this term or divide by this area here and multiply this area, or simply use the term that is the wrong direction. Okay, but if you actually multiply this out, you then get the right term, right? So this here is way more intuitive, this equation at the bottom, because like it says the total energy over time, which is radiosity times area, equals the total emitted energy times area plus the reflectance plus all the emitted areas times all, plus all the emitted radiances times all their areas times the right form factor, right? This is now from JI. So this here is way more intuitive than that one, but this here is simpler, so everyone uses it. But you have to keep in mind, you have to switch direction, which is super unintuitive, but that's still the way it is. Okay, so that's just the direction of the form factors remark. Okay, so now we're almost done. Let's just now that we've done all this crazy math here, let's just see what we can do with it in the end. Okay, so what we've got in the end was this very simple equation here, right? I mean, and that's not very scary. It's just sums, right? It's sums, well, and a few products. But it's actually very simple. There's two issues with that. So one is, well, of course it's simple because we packed all this crazy complexity into these terms f. So we've just factored anything that looked scary, including cosines and integrals and all this. We just included that into a factor and called it conveniently Fij, which happens to be in the wrong direction. But anyways, we've just integrated that into this one term. And on the other hand, so that's trickiness one. Trickiness two is we've got this unfortunate fact that we can't just solve this equation. Why? Because it says Bi equals some constant. I mean BIE. That's just an emissive term. That's probably 0 for most patches except for the light sources. So never mind that. That's okay. But plus the sum over all patches, and unfortunately, sum over all patches includes BI. Okay, so while we do not see this here, it's on both sides. Okay, and even if we would ignore it, we could say, well, a patch doesn't influence itself, who cares? Well, but still it would say BI depends on all the others. Okay, so we need to compute all the others first. Okay, well, whatever. Let's compute the other first. Unfortunately, all the other depend on BI. Okay, so you see the problem here? It's an implicit equation. Unfortunately, BI depends on BI one way or another. Okay, so that's not cool. How can we possibly solve this? Well, it turns out mathematicians have solved this long ago. It's called a system of equations, right? So we can solve this by just solving a system of equations. The question that is left, how can we compute those Fij's? Okay, the rho i's, again, are constants. BIE are constants, so those are easy going. How do we compute Fij's? And that I'll talk about on Thursday morning in the next stream for advanced image synthesis. Okay. Any questions? Any questions for today? Okay, it doesn't seem to be the case. Okay, I hope I didn't throw anyone off by not realizing that the cosine of half pi is 90 degrees, cosine is 0. Okay, but ignoring that glitch, I hope that you can we're able to follow the basic idea here, and well, you can always review the stream to go over the details. If you just go over the details a couple of times, maybe you'll probably notice that it's not a big deal. Okay, so there's a question, cool. So that we do the Fij the other way around is just to well, yes, in a sense you could say, yeah. Well, it's not just a simplification, it also, again, makes the formula more general because it doesn't contain the areas in there, right? Which is not entirely true because F contains the area, right? But yeah, so we're just interested in computing the radiosity, and then we'll just later on weight them with the area. And for the computation, since the area is the thing we know, right? The unknown are the BI. So we're interested in computing the unknowns, and for that purpose, we of course simplify the function as much as possible. And that simplification leads to the somewhat unintuitive Fij thing, which curiously hardly anyone notices. So if anyone's watching this and attending a different computer graphics class and someone teaches you radiosity, challenge your teacher and ask them, like, isn't Fij the wrong direction? Just check for the reply. It's probably a curious thing. I mean, I talked with colleagues for years about this thing that I found that this is awkward, that it's the wrong way. And a lot of folks know this, but it happens to be that at the lab where I was working at that time, we had to figure this out. But it's still interesting. But yeah, so the bottom line is the simplification leads to the fact that you have to switch this direction, which makes this function seemingly unintuitive. I should probably put it like this. It seems unintuitive, but it's not. The thing that makes it seem unintuitive is the fact that we compute a quantity that's somewhat unintuitive, right? Because the radiosity is this per area thing. And while this is very general and useful, the more pers you throw in a thing, the more useful it gets from a physical, mathematical point of view, but the less intuitive it is. Okay, just take something as simple as direction, speed, and acceleration. Okay, or distance, speed, and acceleration. I mean, distance is easy, right? 5 meters. Okay, it's easy. You can easily measure them. You can look, oh, okay, well, that's 5 meters. Okay, so how does 5 meters per second look? Okay, so that's probably harder, right? So how does an acceleration look, right? I mean, look at the unit, like meters per second squared, right? So it's the more pers you add, the less intuitive the whole thing gets. And here's the same. Okay, so the quantity itself, radiosity, is not super intuitive, and just pretending it is creates this sort of issue with the direction. That's at least my take on this. Right? So maybe I'm the only one who has a problem with this direction thing. But again, that's why I say challenge your teacher, asking in which direction the Fij goes, or asking for a definition of what Fij is. Like what's the intuition, and that's again the amount of energy from I to j and not from j to I. Okay, it's probably a little bit overstated here, so it's not a huge deal, right? I think I make it pretty big because it created an impression on me decades ago, and now I bother students for years with that. Talking about bothering you, 5 minutes over time now, so I should probably stop here. So that's it again for today. I'll continue with or finish that part Thursday morning, early in the morning. But if you don't want to get up that early, no problem. You can still watch the video on demand. That's it for today now. Thanks for attending. As usual, see you again in one of the following streams, either on Thursday morning or any of the other streams. Until then, if you can, get vaccinated and stay healthy. Bye-bye.